the work for the anchor should be super straightforward. The anchor has all of its mass at one spot, right? Essentially, all of its mass is centered at its center of mass. The work for the anchor is just going to be the weight of the anchor, which is 100 pounds, times the distance it moves, which is 50 feet. So the work done lifting the anchor from a depth of 60 feet to a depth of 10 feet is going to be 5,000 foot-pounds. Okay. But the work for the cable is harder because unlike previous problems, well, so there are two ways we can do the work for the cable. One of them is really kind of easier. One of them is more challenging. And I feel like they're both challenging, really. So the way I want to, so in the past when we had a cable, what we've done, and this is kind of the harder way of doing it, I'm going to do it both ways so you guys can see the difference. So what we've done before is said, okay, I'm going to take a small piece of the cable that has a length of dy, and the force or the weight of that cable. So the weight for that cable that has a length of dy is just 2 pounds per foot times dy feet, or 2 dy pounds. That's how much that piece of cable weighs. And then we're going to ask if that piece of cable is at a height of y, how far is it going to travel? And this is where things get a little bit more dicey. So most of the cable is going to say, well, if it's at a height of y, it's going to travel up to a height of 50, a distance of 50 minus y. So for most of the cable, the work that's done lifting it from where it is to the depth of 10 feet is going to be the integral of, sorry, it's not going to be the integral yet. We're not at the integral yet. It's going to be just the force times the distance. But here's the problem. Not all of the cable moves 50 minus y. The cable, right, because we're only going to a depth of 10 feet. So the problem is that well, first of all, this cable up here, right, we don't even worry about. Lastly, that's not entirely true. Didn't think about that. Let's see what I missed too. That's where things get confusing. Yeah, we're good. Okay. Okay. So the problem is that this bottom 10 feet of cable here, right? That bottom 10 feet of cable, oh yeah, right, we're good, is going to come up to like, sorry, I know that. Sorry, I found my mistake. My mistake is it's not 50 minus y, right? We're not raising everything up here. All of this cable is going to get raised up to the boat. Sorry about that. So it's actually going to go all the way to the top. This is why I don't do it this way, because this is the more confusing way. So all of this cable is going to travel 60 minus 1. Sorry about that. So anything that's above a depth of, 10 feet above the bottom, anything that's up here is going to travel 60 minus 1. Right? If you're at a height of 15, you're going to travel 60 minus 15, which is 45 feet to get to the top. But if you're down here, you're not going to make it all the way to the boat because you are more than 50 feet below the boat and you're only raising the whole cable up to a depth of 50 feet high. So the problem is this integral will get you the work that's done moving any amount of cable that's above here. So you do the integral of that from, well, let's see, we've got from y equals 10 to y equals 60. But then for this cable down here, all of that cable down there is just going to all move 50 feet. right? Because this is going to move up to the top, this is going to move up to right there. So you're going to add on that amount of cable, which is 10 feet of cable. It weighs 2 pounds per foot, and it's wow, 10 feet of cable to, oh, it's going to move 50 feet. 10 times 2 is 20, 20 times 50 is 1,000. And sorry, I missed something wrong. Okay, so Daniel, all we've done so far is we've talked about how one way to calculate the work done lifting up the cable is to say this top 50 feet of cable, it's all going to move to the top of the boat. So that cable, the work done for it is going to be its weight, distance it travels, and then we're going to integrate from 10 to 60. And then for this last bottom 10 feet of cable, all that bottom 10 feet of cable is just going to move 50 feet. So it's going to, so the work of that is just going to be its force, which is its weight, times the distance it travels, which is 50 feet. Yeah, it's a former quiz problem. So then this integral here is the integral from 10 to 60 of 120 minus 2y dy. You end up with 120y minus y squared from 10 to 60. And I know we're getting a little bit, sorry, it's a little bit messy here. Plugging in 60, you get 120 times 60, which is 7,200, minus 60 squared, which is 3,600, minus plugging in 10, you get 1,200, minus 10 squared, which is 100. And that's going to be 7,200 minus 3,600 is 3,600 minus 1,200 plus 100, and then plus this 1,000 over here. That's going to be 2,400, 2,500, 3,500, which is what it should be. Okay, this is the less good way to do it. But I want to point out because I want to show you there is another way. So one way of thinking about doing a work for a cable or some like rope of a uniform density is to think of the weight being some small piece of the cable and the distance travels being how far that's all going to move. There's another way. There's a better way. There's a way, I should say, there's a way that's better if your cable's not being pulled all the way up to the top. And this is the way I did it in the
James,
yes.
I was wondering, the 7,200 minus on the other side. What was that? It was 3,600 minus 1,200, and then it was plus 100.
And then plus this 1,000 right here.
Oh, okay.
Right, that 1,000 is the bottom 10 feet. The work done for that.
Okay. Yeah. Okay. I just wanted to clarify.
Sure. Okay, the other way to think about this is to say, okay, here's our cable, 60 feet long, y equals 0, y equals 60. And here's what we're going to do. We're going to imagine the cable moves from, say, being this long to moving up just a tiny bit to being, right, we pulled up just dy's worth of the cable. So we were moving the cable up, we pulled it up just a little bit. Okay, so what we're going to do is we say, instead of thinking about dy being the weight of the cable, we're going to say all of this cable, and it's essentially the same length as that because dy is a very, very small amount. All of this cable moved the distance of dy. So now the work is still the force times the distance. But now the force, or the weight, is the entire weight of the cable. So that force is the weight of the cable. Okay, so now, if we're thinking about this cable being at a height of y, that means there is 60 minus y feet of cable left. So the weight of that cable is 60 minus y feet of cable times its density, which is 2 pounds per foot. That's how much that length of cable weighs. If it was all the way extended, it would be the total 60 feet of cable times 2 pounds per foot, which would be 120 pounds. Okay. The distance it has to travel, well, we're moving all of this cable up dy. So then we're going to find the total work. We're going to say, okay, we're going to do the integral. We're going to add up all the work done of 60 minus y times 2 times dy. And now my limits of integration we have to think about. So the cable starts way down here. The cable starts that way down at y equals 0. Right, when y equals 0, the cable is 60 feet long. We move that 60 feet of cable just a little bit. And then when y is a little bit more, like when y is 1, we move that 59 feet of cable just a little bit. But we're only moving the cable up to y equals 50. Right, we're not moving it any further than that. So we're only moving it up. We're only moving all this cable 50 feet. Right? We keep doing this little incremental moves up until the bottom of the cable gets to be 50 feet high. We start with the bottom of the cable being at y equals 0. We end with the bottom of the cable being at y equals 50. And this is going to be the same as what we did before, with, in my opinion, less work. Maybe not really. Anyway, 120, integral of 120 is 120y. Integral of 2y is y squared. We go from 0 to 50. 120 times 50 is 6,000. And 50 squared is 2,500. And you plug in 0 and you get 0. And 6,000 minus 2,500 is 3,500. So this is in my opinion, the preferred way of thinking about the work done for a cable or for a rope, whatever, especially when you're not pulling it all the way to the top. Are there questions about this?
So the distance is dy?
Right. So we did this 2 different ways. In this first way, distance that this little piece moved was 60 minus y. And the weight of this little piece was dy times 2 pounds per foot. Whereas doing it this way, this big piece moved dy, and this big piece weighed 60 minus y times 2 pounds per foot. That's the difference. You could also do this for a problem where it wasn't quite so bizarre. For example, let me show you one more example just so we can all be maybe slightly more clear on this. If you, let's say you had a 100-foot rope and it weighs, let's say it weighs, I don't know, 20 pounds is too much. Let's say it weighs 5 pounds. Let's say you've got some of that like magical elfin rope they use in The Hobbit, right? It's like super light, unties itself. Okay, so you got a 100-foot rope, weighs 5 pounds, and you want to know how much work it takes to pull it all the way up to the top. So we're at the top up here at y equals 100, and the bottom rope's down here at y equals 0. Normally, the way I would do this would be kind of the quote unquote, what I think of as the usual easier way, where I think of, okay, I've got this amount of rope. So the force of the rope, AKA the weight of the rope, is just, or I should say the force. So I should really say the force is the weight of the small piece of rope, which in this case is, okay, that rope is dy feet long times the density of the rope. The density of the rope is 5 pounds per 100 feet, or reducing that fraction, 0.05 pounds per foot. Canceling the feet, this little section weighs 0.05 times dy pounds. That's how much that section weighs. How far is that section going to travel? Well, it's y high. It's going to travel 100 minus y. So the total work, and so the distance is 100 minus y. So the total work is going to be the integral from, right, my pieces are as low as 0 as high as 100. It's going to be the integral from 0 to 100 of my force. I'm going to write my distance first. My distance times my force. I'm not even going to finish this because I don't need to. Let me show you why. The other way we're going to think about this is you've got this length of cable, and it's going to move up dy. So now for that length of cable, what's the force? Well, it's the weight of the whole length of cable, where again it's y high. Well, that length of cable is its length, which is 100 minus y, times its density, which is again 0.05 pounds per foot. And the distance it's going to travel is going to be dy, right? We're moving it just a little tiny dy. So then the total work is going to be the integral of the force times the distance. Well, let's do the distance first. The distance, dy, times the force, which is 100 minus y times 0.05. That's right. But look, those integrals are the same. Yeah, this right. So that's what's going on in this less complicated setup where you're just pulling the cable all the way to the top. Setting it up either way, actually, thinking of it either way, results in the same exact setup. The difference is in the previous problem we did, right? We weren't pulling the cable all the way to the top, and so that resulted in a very kind of different situation. So you can think of these cable problems either way, and I will tell you generally, this way where you're thinking of the entire piece of cable moving a little bit dy, that is the way of thinking of it that is easier to apply to more complicated examples. Whereas this way of thinking of it, even though to me this feels easier to think of, this is less easily kind of made to work for more complex situations. Okay. So that's all I wanted to say about that. If you have any questions, I'm happy to address them before we move on to integration by parts all the time. I assume that's what you guys are doing, right? We're definitely talking about integration by parts now. Yeah, we are. Okay. So hearing no questions, let's go ahead and move on to talking about integration by parts. Again, if you have questions, let me know. Just wondering, can we also do some exponential changes problem? Exponential changes. I'm not sure. Let me take one quick look. Sorry, I meant to look at what each of your teachers is doing as far as what your homework looks like, but I forgot to. If you will, Frank, I got busy doing other things. Oh, okay. Oh, I'm sorry. Integration by parts, yes. So I kind of forgot we're still talking about differential equations. I kind of, sorry. All the classes, the material starts to just kind of blend together. You're like, oh, we did this in this class, or we did this in another class, and you start to forget, or at least if you do, if you're an old man like me, you start to kind of forget what you've done in each class. So let me grab these homework assignments very quickly here, so that I can kind of make sure I'm not doing something super crazy. Yeah, let's see here. All right, one sec. Let's do that. Do that. That's your problem. Okay. Sorry, sometimes, are we going to focus on homework? Well, that's what I was just kind of looking at for both of them. Because I know her homework 5 is due today, right? So let's take a look at homework 5 real quick. Why do you not want to show me homework 5? Okay, there we go. So homework 5, oh yeah, it's all these differential equations. Okay, and so here's what I'll say. We can definitely look at some differential equations, but we're not going to see each other again until Tuesday. And I bet you're probably going to talk about some integration by parts before I see you again. So while I'm certainly happy to look at some differential equation stuff, I feel like we should spend at least maybe 45 minutes to an hour on talking about integration by parts. But let's go ahead and look at, let's see. Let's go ahead and look at some more. Oh yeah, I can't open homework 6 yet either. Whoops, don't quit. No, don't do that. I hate it when you accidentally hit Control Q instead of Control W. It's the worst thing ever. You're like, no, all my tabs. Okay, but let me look at also the other guy here. Why are we having problems? Okay, here we go. Sorry, usually I pulled their homework up and looked at it ahead of time, but I just got busy doing other stuff. Okay, so all right, everybody's still just looking at wacky integrals, and okay. So yes, let's do some y equals y not e to the kt ones. And 11 to 15. Okay, let's take a look at Schulten's 11 to 15. Of course, they're not numbered. Let me grab them. 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay. So we can definitely look at some problems like this. Let me grab. Let me make some approach equations are fun. So I also imagine all of you will get to take a Math 22B, which is all about differential equations all the time. So let's look at 514. I want to pick some examples that maybe aren't exactly from your homework, just to keep it a little bit more fun. Oh, that's crazy stuff. Okay. We really like to do it this way. All right. Okay. Anyway, let's get going. Sorry, that was a quick diversion there. So I'll have to say, Katie, I'm not exactly sure what you mean by exponential change problems. Like, is there a specific problem that you're kind of thinking of for that? Because I guess, okay. I see. Okay, sure. We can do, yeah. I've got one. Never mind. I figured that. I guess, yeah, the weird thing about, to me, the strange thing about asking these radioactive decay problems, it feels, yeah, it's kind of like, I'm surprised your teacher are asking you these radioactive growth or radioactive decay or exponential growth problems, because they're kind of more covered in 21A. Not that doesn't mean we shouldn't talk about them, because we're obviously being asked about them. So here's a couple problems. Let's say we have, sure, I'm just going to make stuff up. An unknown radioactive element. Decays by, let's say, 30% over, I don't know, 50 days. I want to ask a few questions. What's the half-life? How long until only 10% of it remains? And how fast is it decaying when 25% of it is left? Okay, all of these require our knowledge of this differential equation. So the differential equation that I think we talked about last time that is modeling this exponential growth and decay is that dy dt is equal to k times y, right? The rate of growth or decay is proportional to the amount of stuff you have left. This is always the differential equation we're using whenever you're talking about exponential growth or exponential decay. We're talking about something's growth rate being proportional to how much stuff there is left. Like the oil pumping problem, where oil is pumped continuously at a rate proportional to the amount that is left. This is the differential equation we're talking about. So we don't know a whole lot here, but what we do know is the solution to this. The solution, the general solution is y equal to ce to the kt. I know that in Schulten's notes, she used a negative k when it was decay. You don't have to do that. And I wouldn't recommend doing that personally. But we don't even know how much we're starting with. So if you don't know how much you're starting with, and you're dealing with percents, you can make up any number you want. And I'm going to pick 100, and you're going to pick 100 too, because it's the easiest thing to pick. So we're going to say that we're starting off with 100 units, grams, percent of the stuff we're starting with of radioactive material. Great. And actually, I like to make a little table to figure out what I'm trying to do. So here's my table. I know that time equals 0. Sorry, not time equals 0. I know that at time equals 0, I have 100 whatevers. And then I want to know how much I have or what the half-life is. So I want to know at what time do I have half the stuff I started with. I also know that it decays by 30% over 50 days. So I know that 50 days later, I have 70% left. Let's see, I'm also going to be asking how long until only 10% remains. So I want to know what time it is when there's only 10% left. And then I'm also going to ask how fast is it decreasing when 25% is left. So I'm going to ask when there's 25% left, not what time it is, but what is dy dt equal to? Right, because that's how fast it's changing or decreasing. All right, we got our work cut out for us. I think I can erase all this stuff though, because I've caught it all in this table here.
I'm sorry, a quick thing. How do you know that dy over dt is ky? Because it didn't explicitly say it's proportional.
Right, and that's an excellent point. So we are assumed to know that if someone is talking about radioactive decay or exponential growth, that we know that the rate of decay is proportional to how much radioactive material there is. So the more material you have, the faster it's going to decay, and the less material you have, the slower it's going to decay.
So we could just assume that unless stated otherwise.
Right. It's something that is, it's not that just that we're assuming it is always assumed when you're talking about radioactive material specifically. If someone says you've got a radioactive thing, the automatic assumption is two things. I mean, it's really one thing. The automatic assumption is that the rate of change is proportional to how much stuff there is. And then that goes hand in hand with the model y equals c to the kt.
All right, for sure. Thank you.
But the really fair point, Katie, like we're not saying that the rate is proportional. It's that we are assuming from science that, oh yeah, you've got radioactive stuff. it's decaying at a rate that's proportional to how much stuff there is. Okay, so we've got all that over there, so I'm going to erase this. Our first job always, when we're dealing with solving a system like this, is to figure out what CU and K are. We already figured out what C is by just choosing 100 to be the starting amount. If they give you a starting amount, that's what your C value is going to be. And then I'm going to plug in my other kind of known piece of information to figure out what K is. So I know that when time equals 50, Y equals 70. So 70 equals 100 e to the K times 50. Divide both sides by 100. 70 over 100 is 0.7. That's equal to e to the 50K. Take the natural log of both sides. Natural log of 0.7 equals the natural log of e to the 50K. Natural log of e to a thing is just the thing. And then divide both sides by 50. So the K is equal to the natural log of 0.7 divided by 50. Great. So now we can rewrite our model as y equal to 100 e to the K, which is natural log of 0.7 divided by 50 times t. Great. I will point out this K value is a negative number, as it should be when you're finding exponential decay. All right, now we're going to answer the other questions. So the other questions were, what's the half-life? I think I can erase this, I guess. So to find the half-life, we're just setting y equal to half the stuff we started with. So we're just solving the equation 50 equal to 100 e to the natural log of 0.7 over 50. Okay, so take this, divide both sides by 100. 50 over 100 is 1/2. It's equal to e to the natural log of 0.7 over 50 times t. Take the natural log of both sides. Natural log of 1/2 equals the natural log of e to a thing is just the thing. So it's equal to the exponent here, which is natural log of 0.7 over 50 times t. And then t is equal to the natural log of 1/2 divided by the natural log of 0.7 over 50. More generally, and this is right, this is the half-life. The half-life is always equal to the natural log of 1/2 divided by k, assuming that your k is negative like we've done here. Or if you want to rewrite this, you can say the natural log of 1/2 is the natural log of 1 minus the natural log of 2, and the natural log of 1 is 0. So this is also can be written as the negative natural log of 2 all divided by k, which might look more familiar to you. She probably wrote hers as the positive natural log of 2 divided by k, because her k number is actually a positive number, and then she's saying she has e to the negative k to make it negative. Just be aware, right, of what's what. So that, and then I would simplify this. I would flip and multiply and say that t is equal to 50 times the natural log of 1/2 divided by the natural log of 0.7. Okay, I don't really want to do this one here that I wrote. How long until only 10% is left? It's literally the same work we did, except instead of there being 50 left, there's going to be 10 left. So 10 divided by 100 is 1/10. So you're going to get a 1/10 there. You're going to get a 1/10 there. You're going to get a 1/10 there. That's the very, very, very lazy way of answering the second question, right? But it's the same sort of question, right? You're just asking how long until, first we asked how long until there's 50 grams left, right? The half-life is how long until there's 50% of what you started with. And the second question is, how long until there's 10% left what you started with? Okay, so set. Then that you have to be 10% of what you started with. The last question, and this question goes more towards the oil pumping question, is how fast is the radioactive material decaying when there is 25% left? So then we have to say, well, if you're asking how fast something is changing, you're asking what the derivative is. Well, the derivative is k times y. And that type of question is actually important, why you know what differential equation you get when you say something's changing at a rate proportional to how much stuff there is. Right? Nowhere in this problem did they say dy dt equals k times y. We have to know that. And then say, okay, well, I know that dy dt equals k times y. I know that k is natural log of 0.7 divided by 50. So I want to know how fast this thing is decaying when y is equal to 25. I'm literally just going to throw y equal to 25 in there. So you're going to get dy dt is going to equal natural log of 0.7 divided by 50 times 25. Or simplifying, it's going to be the natural log of 0.7 divided by 2. So notice here, you are going to get a negative number. The natural log of 0.7 divided by 2 is about negative 1.78. Sorry, negative 0.178. Oh my God, negative 0.178. And the units of that would be, well, whatever units your thing was measuring. So if we were measuring in grams, right, if we started with 100 grams, we would be decaying by 0.178 grams per day. Or if we were talking in percents, we would be, at this moment, we'd be decaying by 0.178% per day. So you can either say you're changing at negative 1.78, or if you say you're decaying, you usually say it as a positive. You're decaying at positive 0.178 grams per day. So yeah, that's kind of one of those questions. Let's look at a couple more differential equations, and then I think, and yeah, we should talk about integration by parts. It's not a small thing. And let's see here.
Sorry, quick thing, but do you mind flipping the board over again? I didn't catch that last part.
All right.
Is that around negative 0.178?
Yes.
Thank you.
You're welcome. All right. So let's see one more thing here. Sorry. Yeah, they're giving us. Sure. Let's say we had something like the following. Let's say we had 1 over 2x dy dx equal to e to the x, e to the x squared over y. Sure, that looks fine. And we have an initial condition that, careful here, y of 0 let's say y of 0 is equal to -3. That's going to be good. All right. We're going to look at two different distributions, actually. We're going to look at y of 0 equal to -3. We're going to look at y of 0 equal to +5. We'll do both of those at the end. So I want to solve the system of differential equations. It's separable. I've got dy on top over here, so I should bring all the y's to this side. I've got dx on the bottom over here. I should bring all the x's to that side. Yeah, things should still work out just fine. Okay. So I'm going to say that, yeah, y times dy should equal 2x times e to the x squared dx. Right? I multiply both sides by 2x dx, multiply both sides by 1.
James, I have a quick question. Sorry. So you always want to have your y's on the left side and your x's on the right side? It's like a general equation, pretty much.
It's the more general statement is that if your derivative is on the left, you want the things on top to basically you want the variable that's on top to be on the side that it's on.
Okay.
So if someone was being annoying and wrote like dy dx equal to, I don't know, y cubed over x squared, then I would want my y's on the right. And my
Okay. For sure.
But yeah. So then we're going to integrate both sides. The integral of y is y squared over 2. And now, I think we can do this integral without actually doing the u sub. I think we can all see that if we did the u sub, u would be x squared. The du would be exactly 2x dx. So we'd be integrating e to the u du, which would equal e to the u, which would equal e to the x squared. Or, if you prefer, what's the derivative of e to the x squared? Oh, it's e to the x squared times the derivative of x squared, which is e to the x squared times 2x. But you could, right? We could totally say u is x squared, du is 2x dx. That integral becomes the integral of e to the u du, which is e to the u, which is e to the x squared. You could do that. I'm just saying, a lot of these problems have so many moving pieces that if you can see how to do an integral without actually having to write out the u substitution, it's usually pretty okay to do that. So now is where you have to be careful about deciding when to find your c value. And I might find it right now. I picked values that didn't try to be quite as nice as I wanted them to be. That's all right. So I'm going to pick. So let's see. So let's do this one here. And this should work. So y of 0 is -3. I'm going to have -3 squared over 2 equal to e to the 0 plus c. 9 over 2 minus e to the 0 is -1 equals c. So c equals 7/2. Okay. So then, solving for y, we multiply both sides by 2. You get y squared equals 2 e to the x squared plus 2 times 7/2 is 7. I might actually say that maybe it would have been better to solve for c right here. Right? If you multiplied by 2 first, you would have had y squared equals 2 e to the x squared plus a new constant. And then if you plug in 0 for x and -3 for y, you get 9 equals 2 plus c, and then you can solve for c being 7. That might be a little easier. And then solving for y is equal to, so this is where something interesting happens. You get the square root of 2 e to the x squared plus 7. But the thing is, if you plug in 0 for x, what do you get for y?
You get -3.
You don't get -3 the way I've written it. You plug in 0, what do you actually get? If you plug in 0 here, what do you end up getting?
Square root of positive.
Right, the square root always gives you a positive answer. So the thing is, our answer to this function actually is that y is equal to the negative square root of 2 e to the x squared plus 7. Because of our initial condition being equal to a negative number. On the other hand, if we were using the other initial condition, where we have y squared equals 2 e to the x squared plus a constant, right? I'm going straight from this step where I haven't solved for my constant yet. If I plug in y equals 0 and, sorry, if I plug in x equals 0 and y equals 5, I get 25 equals 2 e to the 0 plus c. So that's going to give me c equal to 23. And then my solution is going to be y equal to the square root of 2e to the x squared plus 23. And it is the positive square root. Because when I plug in 0, I want to get y equal to positive 5. So specifically, right, when you're solving something like y squared equal to whatever, and you get y equal to plus or minus the square root of whatever, you don't actually get plus or minus. It's, or I should say, it's one of those exclusive ors, meaning it is one or the other, but not both. You have to pick whether it's positive or negative, and it's wholly determined by what your initial condition is.
Oh, so James, so pretty much what you did in this question is you created two conditions?
Right, two different initial conditions. So technically it would be two different problems.
Yeah, okay, so yeah, okay, because I got confused because
the answer would be this function.
mm-hmm.
For this red initial condition, the answer would be this function.
Okay, so for like the green part, James, you put the negative to make it turn into -3.
Right, because because when you take a square root, of a number, you always get a positive.
Yeah, okay, yeah, because you have to. It's like, yeah, I get it now. You have to pretty much kind of fix up the equation yourself to make it true.
And it's because, right, I mean, and the reason we get a positive answer when you take a square root isn't a good reason. It's because we all decided, or really mathematicians decided, we want the square root of x to be a function. Right? When I take the square root of x, I don't want to say the square root of 9 can be 3 or -3. So, right, so that when I graph this, I get a nice function that passes the vertical line test and not some garbage that doesn't pass the vertical line test. Right, so that we really have said, right, it's not just like it always worked this way. We really said, well, I know the square root of 9 could be 3 or -3. But we, as a mathematical community, said we want it to always be one, not both. So we're going to make it so it's always the positive square root, so that this is a function. And so then if you want it to be negative, you have to tack on a negative. That's what's happening there. Okay. Yeah. Let's talk about integration by parts, because it's definitely important. So I know you might not have gotten there yet, but it's definitely coming your way. So let's go ahead and talk about it. Let me go back to my notes here. And I don't think I started talking about integration by parts on Tuesday, but I honestly don't remember. So bear with me if I repeat. Oh, okay, good. So there is a bit to cover. So integration by parts, which we usually abbreviate as IBP, integration by parts, is for basically we use it when we have what I like to call a mixture integrals. Meaning you have a mixture of two different types of functions. Specifically, usually we have mixture integrals and U sub doesn't work. So for example, the integral of x times e to the x squared, which I'm sure we've done like a bajillion times. This is my idea of a mixture integral. It's a mixture because here we have a power of x. Here we have an exponential. That's a mixture of things. Okay, that's all right. Sometimes people mix up, I often mix up the words, the names integration by parts and partial fractions. Not that I think that's what you've covered, just I often make that error, so be aware. I will usually correct myself though. So sorry, my coworkers are commenting on the picture I shared with them as well. My coworkers really like the boat shark picture that one of you guys drew in the quiz. I also really liked it. I was sharing with them. So,
I'm glad you appreciated it.
yeah, it was a great picture. So this integral here, we can do with a u substitution. And so whenever you see a mixture, you should always ask yourself first, can we do a u sub? U sub is almost always going to be easier. Yeah, we can totally do a u sub here. U equals x squared, du is 2x dx, 1/2 du is x dx. This becomes the integral of, let's see, I got a 1/2 integral of e to the u du, which is 1/2 e to the u plus c, which is 1/2 e to the x squared plus c. Easy. But sometimes we're going to have mixtures where you can't do u substitution, like the integral of x times e to the 2x. Looks very similar, but is very, very different, right? If you do a u sub here, it's not going to work out. Letting u equal 2x, you're not going to get rid of the variable here, right? If u equals 2x, du is 2 dx, and then 1/2 du is dx. So great, I can rewrite this as the integral of, well, dx is 1/2 du, great. E to the 2x is e to the u, and x is u over 2. This problem didn't really change. It's still essentially the same. So what we have to do here is use a process called integration by parts. And did we talk about how it was derived last time? I don't remember. I think we did. It's probably worth saying it again. So integration by parts comes from the product rule. If you take the derivative of u times v, you get u prime v plus u v prime. Or using slightly different notation, uv prime is equal to du dx times v plus u times dv dx. And then if we integrate both sides, well, the integral of the derivative is just the function itself. And here we're going to integrate v times du dx with respect to x. And here we're going to integrate u times dv dx with respect to x. But the dx's cancel. So we have the integral of v du plus the integral of u dv. And then we're going to isolate this so that the integral of u dv is equal to uv minus the integral of v dv. Or as I will often say, the integral of u dv is the ultraviolet super voodoo. So integration by parts, ultraviolet super voodoo. Super easy to remember, I know, right? The point of this, and I feel like I said this before, but I'm saying it again. The point of this is that when you decide what u and dv are over here, and you rewrite it as uv minus the integral of v du, we get to then have an easier integral, or at least that's the point. So here, we're going to choose a u and a dv. And the nice thing about this is once you choose what u is, dv is automatically selected for you. And we want to pick u so that its derivative gets simpler. So does it make more sense to pick u equal to x or u equal to e to the 2x? Well, the derivative of x is 1. That got simpler. The derivative of e to the 2x is e to the 2x times 2. That didn't really get simpler. So we're going to let u equal x. dv should also be the most complicated thing that's easy to integrate. And the integral of e to the 2x is not that hard at all. So once you pick u equal to x, dv has to be literally everything else. So we're going to get du equal to dx, and v is going to be 1/2 e to the 2x. And now we're going to say the integral of u dv is equal to uv minus the integral of v du. And look, this integral is easier to deal with. We know how to integrate 1/2 e to the 2x. This is x times 1/2 e to the 2x minus the integral of e to the 2x is e to the 2x divided by another 2. So I get 1/2 times another 1/2 times e to the 2x. So that's the very kind of basic idea. I wouldn't say it's basic, but that's kind of the base level idea here, is that you're taking an integral that's complicated, a mixture of two types of functions multiplied together. And we're rewriting the integral so that the part we have to integrate gets easier. Let's look at some more examples. But again, and this is kind of important, it's on us to identify when we should be using integration by parts, when we should be using substitution, when we should maybe be using something else. So sorry, my friends are writing other things. So let's look at some other examples here. Let's look at the integral of, say, I don't know, the natural log of x to the 5th power divided by x. First question out of my mouth, can I do a u sub? Is there anything I can let u equal that might make sense? Yeah, we can let u equal natural log of x. du would be 1 over x dx. I've got that. Great. So this is going to be the integral of, let's see, dx over x. That's my du. And natural log of x to the 5th power is going to be u to the 5th. And we're going to integrate. We're going to get u to the 6th over 6 plus c. We're going to get natural log of x to the 6th over 6 plus c. Awesome. On the other hand, someone could ask us to do the integral of x to the 5th times natural log of x dx. And now, u substitution doesn't really make any sense. By letting u equal natural log of x, my du is 1 over x. I still got all this x to the 5th left over. That doesn't seem like it's going to work out so well. So instead, we're going to do integration by parts. Now, how do we choose our u? Do you want to choose u equal to x to the 5th or u equal to the natural log of x? Well, both will get simpler if we differentiate them. Right? The derivative of x to the 5th is 5x to the 4th. The derivative of the natural log of x is 1 over x. The other question is, if you pick one of them, the other one's your dv. So what's easier to integrate? X to the 5th or the natural log of x? Well, I know how to integrate x to the 5th. Do we know how to integrate the natural log of x? We might not yet, because it actually requires integration by parts. And so here's a kind of a shortcut for how you decide what you're going to pick for u. Your u, you're going to choose in the order of the acronym LIAT. First, if you have a logarithm, you're going to pick that for u. If you don't have a logarithm, you're going to pick an inverse trig function. If you don't have either of those, you're going to pick a power of x. If you don't have either of those, you're going to pick a regular trig function. If you don't have any of those, it's probably not integration by parts. But occasionally, you might pick an exponential, like e to the x. There is one crazy example where you do pick u to be kind of an e thing. But most of the time, if you're doing integration by parts, You're never picking u to equal e to the something, with very, very, very rare exception. Okay, so here we're going to make u equal to the natural log of x. If you see a problem where you think it might be integration by parts, it's always going to, and you have a log, you're almost always going to think u equal y. Yeah, good call, Katie. I stands for inverse trig. A, so people call A different things. Some people will say it's an algebraic term. I've started saying it's a power of x, meaning x squared, x cubed, x to the 1/2, something like that. Some people use a different acronym and they call it LIPTE, and they just say P is for power of x. Okay, so u is natural log of x, and then once you've determined what your u value is, everything else, including the dx, is your dv. So dv is equal to x to the 5th times dx. Great, the rest is just filling in all the things. The derivative of u is 1 over x, so we get 1 over x dx. The antiderivative of x to the 5th is x to the 6 over 6. Then we throw it all into the ultraviolet super voodoo formula. So this integral is equal to u times v minus the integral of v du, x to the 6 over 6 times 1 over x. Now here's the thing. This second integral here is simpler than the first, but sometimes we actually have to do some simplification to make it easy to deal with. On the previous example, we didn't have to do anything. Integral of e to the 2x is e to the 2x. But for this example, you have to multiply this out or simplify it before you can actually integrate it. But you can't say the integral is like x to the 7th over 42 times the natural log of x. It just doesn't work. Instead, you have to say, oh, this is the natural log of x times x to the 6 over 6 minus, I'm going to factor out the 1/6, and then x to the 6 divided by x is x to the 5th. And then we get the natural log of x. I would probably write the x to, usually we write x to the something in front of the natural, so probably this is x to the 6th over 6 times the natural log of x minus 1/6 times the integral of x to the 5th, which is x to the 6th over 6. And yeah, you could write this term as x to the 6th over 36. Yeah, let's look at some more. So, let us look at, again, what's in front of the natural log of x? X to the 6 over 6. I moved it in front because typically we write, instead of writing natural log of x times x to the 6 over 6, it's kind of more standard to write it as x to the 6 over 6 times natural log of x. That way you're less likely to say, oh, x times x to the 6 is x to the 7th, which it isn't in this case because the natural log of x, the x is stuck inside the logarithm function. Let's look at this last kind of contrast. Yeah. So we have the integral of x times cosine of 4x squared versus, yeah, the integral of x squared times cosine of 4x. So again, both of these are mixtures. I have a power of x times cosine of something. Here I have a power of x times cosine of something. They're both mixtures. I got two different types of functions going on. So here I'm going to think about the u sum. Oh yeah, I can let u equal 4x squared. This du is going to be 8x dx. 1/8 du is x dx. So this integral is going to become the integral, let's see, so x dx is my 1/8 du. And then cosine of 4x squared is cosine of u. Integral of cosine is sine, so we get 1/8 sine of u. Let's see, just 1/8 sine of 4x squared. Let's see. No big deal. On the other hand, this one is a giant pain in the butt, which we're going to talk about how to make it easier in a minute. So if I want to integrate that, I'm going to do integration by parts. I'm going to let u equal, well, according to Lie8, any power of x comes before a trig function. So I should let u equal the power of x. U is x squared, du is 2x, dv is the rest, it's cosine of 4x. And the antiderivative of cosine of 4x is positive sine of 4x divided by 4. Let's rewrite the integral. Our integral is going to equal uv, so x squared times sine of 4x all over 4, minus the integral of v du, sine of 4x over 4 times 2x. Oh, I forgot the dx there. But now, and this is bad news, we have to do integration by parts again. Because this integral, although it's simpler, right, it's a lesser power of x times a trig function, it's still a power of x times a trig function. I would probably factor out the 1/2 and rewrite this as x squared times sine of 4x over 4 minus 1/2 times the integral of x times sine of 4x. So now I get to do integration by parts one more time. So we're going to let, now for this one, we're going to let u equal x. Du is going to be dx. By the way, you never want to let u equal x in a u sub problem because you're literally just changing all the x's to u's and nothing is really different. But it's definitely okay in integration by parts problem to let u equal x. And dv is going to be sine of 4x times dx. And the antiderivative of sine of 4x is negative cosine of 4x divided by 4. All right, so we're going to get this is equal to, I've got still this, x squared times sine of 4x over 4 minus 1/2 times the integral of this is the whole ultraviolet super voodoo. So it's going to be 1/2 times all of that. 1/2 times uv, so x times negative cosine of 4x over 4. I need more room. No, yeah, I need more room. Sorry. Let's try and make it fit. So it's x squared sine of 4x over 4 minus 1/2 times the integral of x sine of 4x, which is my uv. So x times negative cosine of 4x over 4 minus the integral of v du, which is negative cosine of 4x all over 4 dx. Whew. We're not done. We still have to integrate this. So let me clear up some room here. Yeah, let me write it over here. So here's what we get for our final answer. We get, I'm gonna write it kind of this way. We get x squared sine of 4x over 4 minus 1/2 times x times negative cosine, if it's a negative cosine, of 4x over 4. So let's see, negative 1/2 times this is going to give me a positive x times cosine of 4x all over 2 times 4 is 8. And then we have minus 1/2 times minus 1 times minus 1. So it's going to be a minus 1/2 times the integral of cosine of 4x all over 4. But the integral of cosine of 4x over 4 is sine of 4x over another 4 times 4. So, or you can just factor out this 4 here. It's negative 1/8 times the integral of cosine of 4x. And the integral of cosine of 4x is sine of 4x over 4. And then you could write this as minus sine of 4x over 32. So here's kind of the bad news, but don't worry, there's good news. The bad news is if you have to integrate something like x squared cosine of 4x, you're going to have to integrate by parts twice. And more generally, if you have to integrate something like x cubed times sine of x, you have to integrate by parts 3 times. Or x to the 4th times e to the x, you have to do it 4 times. But there is some good news. There is a faster way of doing this. It's called tabular integration. Sometimes it's called vertical integration. Now, this only works for 3 specific types of integration by parts integrals. So here are the 3 types of integrals. We want to, so tabular integration. Which is a faster method of doing these, works for the following types of integrals. The integral of x to a power times sine of a constant times x, or the integral of x to a power times cosine of a constant times x, or the integral of x to a power times e to a constant times x. Those are the 3 types of integrals, and the only 3 types of integrals where a tabular method works. There is one more requirement. P has to be a positive integer. It does not work if P is like a fractional power or a negative power. So here's why P has to be a positive integer. We're going to let u equal x to the power, and then eventually the derivative of that power has to be 0. Otherwise, the process will never stop, right? The derivative of, say, x to the 6th, if you keep taking the derivative, eventually you're going to get to 0. So 6x to the 5th, and then something x to the 4th, and then something x cubed, and then something x squared, and then something x to the 1st, and then something times just a constant, and then 0. But if you have some power that's not an integer power, eventually, right? If you keep subtracting 1, you're not going to get down to 0 as your power. Okay. So let's revisit the problem we just looked at. The problem integral of x squared cosine of 4x dx, which I believe is what we were doing. Let's double check. It is. Okay, so here is the magic. The magic is you're still going to pick your u and your dv the same way. If u equals x squared, dv is cosine of 4x. Yes. And you're not going to write any of the rest. What you're going to do instead is you're going to make a table. That's why it's called the tabular method. You're going to make a u column, and you're going to make a dv column. And in the u column, you're going to differentiate until you get to 0. Which is why you have to have x to a power that's a positive integer. The derivative of 2x, x squared is 2x. The derivative of 2x is 2, and the derivative of 2 is 0. And you do want to write the 0 because you want to make sure you have the right number of rows. And you need that bottom row where this is 0. And then, so this way you are differentiating. On the other side, for dv, you're going to anti-differentiate. Which again, I don't think this is news to anybody, right? That's exactly what we were doing before. You make your choice for u, you take its derivative. You make your choice for dv, you take its antiderivative. So we're going to anti-differentiate this until we get down to the same number of rows. So antiderivative cosine of 4x is 1/4 sine of 4x. The antiderivative of 1/4 sine of 4x is, well, antiderivative sine of 4x is negative cosine of 4x over 4, so it's going to be negative 1/16 cosine of 4x. And then the antiderivative of that's going to be, well, the antiderivative of cosine of 4x is sine of 4x over 4, so I'm going to get negative 1/64. I'm getting another factor of 4 in the denominator times sine of 4x. Okay, now here's what we do. We go from here over 1 and down 1. Over 1 and down 1. Over 1 and down 1. And the signs always alternate. So it's plus this product minus this product plus this product. So here's what my answer looks like. My answer looks like, right, this integral is equal to x squared times 1/4 sine of 4x minus 2x times negative 1/16 cosine of 4x plus 2 times negative 1/64 sine of 4x plus c. And if we simplify, we get x squared sine of 4x over 4 minus minus is plus 2 over 16 reduces to 1/8, so we get x cosine of 4x over 8, and then 2 over 64 is 1/32, so minus 1/32 sine of 4x, which should be exactly the same as what we got here. X squared sine of 4x over 4 plus x cosine of 4x over 8 minus sine of 4x over 32. Same exact thing. So that's called the tabular method. And it totally works whenever you have x to a positive integer power and either e to the x, sine of x, or cosine of x. Should we do another one? Let's do another one.
Wait, James, I have a quick question. So how come for dv we never go to 0? It's only for you that we want to go to 0?
Well, because we can't, right? The thing is here, dv, when you anti-differentiate cosine, it's never, the antiderivative of cosine, no matter how many times you do it, is never going to be 0.
Oh yeah, that's yeah.
And so really what we're doing is we're just doing this whole process here in a shorter way, right?
Yeah.
So if you look at this process, my first choice, so when I did this, right, I had x squared times v. Well, right, I'm getting x squared, and if this was the dv for this u, this is the v for that u.
Yes.
But then I have to do it again, right? So then in my next integral, I'm gonna actually put things back in here for a second. So in my next integral, where this is sine of 4x over 4, and this is 2x, my next integral, this is my u, and this is my dv. So when I integrate that, I get u times the antiderivative of this, which is v. Well, the antiderivative of that is exactly this. So I'm getting u times the d, right? This is my new u, and for this u, that's dv, and that's v. So I'm getting u times v. And the reason it's a minus is because it's minus that integral.
Okay, and then how come then after we go to a plus?
Because, excellent question. So then for the last one, right, we get to, I'm sorry, I probably simplified more than I wanted to. Yeah, I don't want this 1/2 out here anymore. Sorry. I want so the point is that the reason it's a plus is because it's a minus. Right, that minus sign from here is going to distribute to the new minus sign that's in front of the next integral.
Yeah, that makes sense. So that would that be the case for all like all
Yeah.
problems? It goes like plus, minus, and then plus again?
Whenever you do tabular integration, which again is only for these three types of integrals, always going to be plus, minus, plus, minus, plus, minus, plus, minus forever and ever and ever.
Okay.
It's plus uv minus the integral of the next uv, or minus the integral of v du, which is going to give you minus the next uv, and then it's going to be minus the next one, which is plus, and so on and so on and so on. Basically, this minus sign in your formula keeps on kind of hitting the next one, so it keeps changing, it keeps alternating back and forth between minus and plus.
Okay, that makes sense. Thank you, James.
You're welcome. So let's do it one more, and then we will move it on. So let's say we want to do the integral of x cubed e to the negative 2x. Great, no big deal. We're going to let u equal x cubed, and your dv is going to be e to the negative 2x. And then we're going to start differentiating. So we always start with the u side, because that's going to tell us how many entries we need. So x cubed, the derivative is 3x squared, the derivative is 6x, the next derivative is 6, the last derivative is 0. I need that many entries over here. All right, so we can make you can make it more table-like if you want to, you don't get things screwed up. So the antiderivative e to the negative 2x is e to the negative 2x divided by negative 2. The antiderivative of that is e to the negative 2x divided by negative 2 times another negative 2, which is 4. The antiderivative of that's going to be e to the negative 2x divided by negative 8. The antiderivative of that's going to be e to the negative 2x divided by positive 16. And then it's going to be plus this times this, minus this times this, plus this times this, minus this times this. So we're going to get, let's see, so this times this is going to be negative because of that negative down there. So it's going to be negative x cubed e to the minus 2x over 2. And then this one's going to be negative because it's a minus 3x squared times e to the negative 2x over 4. So it's going to be minus 3x squared e to the negative 2x over 4. And then this one's going to be negative because it's a 6x, it's a plus 6x times e to the negative 2x over negative 8. So it's going to be minus 6x e to the negative 2x over 8. You can reduce that to 3/4 minus 6 e to the negative 2x over 16 plus c. Done. Instead of doing integration by parts 3 times in a row, which would be terrible.
Wait, James, I have a good question. So how did we get a negative x cubed for our first one? Like our first for the green writing.
Because this first one is positive x cubed times e to the negative 2x over negative 2.
Oh, yes.
And I don't like writing negative in the denominator. I want to bring it out in front in the numerator.
Yes. Okay, thank you, James.
Okay. Typically for the e to the x ones, the sign is almost always the same. It's either always negative or always positive. For the sine and cosine ones, it alternates kind of sporadically, because for the sine and cosine ones, this alternates every term, but then the antiderivative changes signs like only every couple other time, right? Like the antiderivative of this is still positive, then the antiderivative is negative, then the antiderivative is still negative. So these don't change in the same sort of way.
Yeah.
Every second kind of changes. Let's see. My voice is getting a little tired. Talking a lot. Where should we go next? What's likely? I guess we should do an interest rate one. So sometimes you have to do integration of parts even when it doesn't seem super obvious. For example, I want to do the integral of the natural log of x. Well, it doesn't look like a mixture. Technically, it's a mixture. As I've got, so here's what you can kind of count. you can kind of count dx as a power of x. Really, so if you really want, you can call this the integral of natural log of x times 1 dx. Sorry, one second. So, we're going to use the LIATE acronym. And we're going to let u equal the log thing. Okay, what's left to let dv equal to? There's not a lot of options. What do we got?
Oh wait, James, before I was wondering if you could re-explain what the LIAT it stands for again.
Sure. So the L stands for log. The I stands for inverse trig. A stands for any power or a power of x or any power of x. T stands for regular trig. And E stands for really it's like e to the x or an exponential. Okay. So in this particular problem, if we've chosen u to be natural log of x, what's the only possible choice for dx? Or sorry, for dv? Well, we've done this. What's left over?
1 dx.
Right. Okay. What's the derivative of natural log of x?
1 over x.
What's the antiderivative of 1?
Just x.
Right. Then we can rewrite this as uv minus the integral of v du. But then these x's cancel. So you get x natural log of x minus the integral of 1, which is x natural log of x minus the integral of 1 is just x. Let's see. That's it. There's your integral of natural log of x. There's a couple other intervals like this. I'll do one of them. We'll leave the other one for you guys to do on your own sometime. So, in a similar way, we integrate the inverse tangent of x. We're going to make the same sort of choice. We're going to let u equal the inverse trig function. Because again, according to LIATE, I should let u be the inverse trig thing, and I should let d be the any power of x thing. Okay. What's the derivative of the inverse tangent? 1 over 1 plus x squared. The antiderivative of 1 is again x. So this becomes uv, so I'm going to write it as x times the inverse of x minus the integral of v times du. Now this part here requires a u substitution. So we're going to do a u sub here. We're going to let u equal 1 plus x squared. Our du is going to be 2x dx. So that 1/2 du is x dx. So then this x dx becomes 1/2 du. And then this is 1 over u. The integral of that is going to be 1/2 natural log of the absolute value of u. And then that's going to be 1/2 the natural log of the absolute value of 1 plus x squared. Since 1 plus x squared is positive, you don't need the absolute value. So this just becomes x inverse tangent of x minus 1/2 the natural log of 1 plus x squared. And that's the antiderivative of the inverse tangent function. It's a little complicated, but it's not too bad. What I'm going to tell you is you can, and you should really, if you have the time, you can do the same sort of process for the integral of inverse sine. And it works out very similarly in that you get a similar kind of thing here. And then this integral, you're going to get something like x times 1 over the square root of 1 minus x squared. And again, you're going to integrate that by doing a u step. But you should try that on your own sometime. How much time you got? Okay, we got some time. Sometimes you have to do a u substitution and then do integration by parts after, which is not my favorite.
Quick thing before the ln part for the last problem, shouldn't it be absolute values? Or
so, generally yes, but 1 plus x squared is always greater than or equal to 1.
Mhm.
The absolute value of 1 plus x squared, since the insides are already always positive, the absolute value of something that's always positive is just whatever is inside it.
I see, thank you.
Cool. Yeah. I will also say though, if you're not comfortable with that, it's really, really, really perfectly okay to leave it as the absolute value. Like if you're not sure, like, oh, is this thing, maybe it's always positive, maybe it's not, I'm not sure. It's always a safe bet to leave the absolute values. And we could totally write it like this and still be 100% correct. And if you're not sure, I would definitely encourage you to leave it like that because it's a safer way to go. Okay, so let's look at this problem. So I'm going to do the integral of, let's do cosine of the square root of x. This does not look good. I don't have a lot of choices. It's definitely, so I would say this actually doesn't qualify as the typical kind of mixture. What I really should say actually is typically to use integration by parts, you have to have one type of function multiplied by another type of function. I guess I mean, you could say, well, James, you just did this last problem. You didn't really, okay, fine. There's some exceptions. But this one, so when I'm kind of out of, when I'm stuck, I usually fall back to u sub. I'm like, okay, well, maybe there's a u sub. Maybe I'm going to try letting u be the inside of the function, because that makes sense to me. U is the square root of x. And then I know that if I find du, I'm going to get 1 over 2 root x dx. I don't have a 1 over 2 root x. So I'm going to do this other thing we do sometimes. When you do a u substitution, like I know I'm not going to get, right? That's not in my integral anywhere. So instead what we do is we solve this for x. And then we differentiate this. Derivative of x is dx. Derivative of u squared is 2u du. And I will also point out, you can get there from here. You can say that dx equals 2 root x dx, du. And then u is equal to the square root of x. So 2u du is dx. Most people find this the more natural way to get there, though, is you take your u sub, you solve for x, and then you differentiate both sides to get dx all by itself. So I'm going to replace this. I'm going to write this as the integral of, so dx is 2u du, and cosine of root x is cosine of u. Oh, now this looks like an integration by parts problem. I have my any power And I have my trig. So I'm gonna so here's the problem. I use my variable u, which is, it's dumb that people decided we're gonna do u sub and integration of parts both using the letter u. It was a poor choice that we made a long time ago, and now we're stuck with it. So we're gonna use a different variable in our integration of parts. Instead of using u, I would use w and dv. So I'm gonna let w equal u and dv equal cosine of u. Then dw is du. And v is the antiderivative cosine, which is sine of u. I need the du here still. So then this integral is going to become this times this, right? It's my w times v instead of my u times v. So here's the thing, right? It's w times v, which is u times sine of u. Minus the integral of v dw, which is going to be sine of u times du. And don't forget the 2 that's multiplying all of this. And now we can integrate that. We're going to get 2 times u sine of u minus the integral sine of u is negative cosine of u. So we're going to get minus a minus a plus cosine of u. Let's see. And then finally we go back and we plug in u equal to the square root of x, and we get 2 times the square root of x times sine of root x plus cosine of root x. All right, I think that is a good stopping place for today. My voice is, I have to learn how to not talk so loud. The problem is I teach in here often, like I'm teaching to a regular classroom. Like I need to project loudly, and I clearly don't. There's a microphone sitting 3 feet away from me right there. I should. So if you guys hear me talking loud, my wife is a little further away. She's like, James, you're yelling. If you hear me talking loud, remind me not to talk so loud because I need to save my voice. So yeah, I will see you all on Tuesday. We'll talk more about integration of parts on Tuesday. I have office hours tomorrow at 11 and at 2 and 11. Yeah, 11 and 2, and we'll see you next week. Have a good week. Also, no quiz this week. Yeah, no quiz this week.
James?
Yeah.
I have a question. So because when we do v, when we do our w times v and then minus the integral, is that just for the integral we just do v times dw?
Right, exactly. It's w times v, because w is playing the role of u, minus the integral of v times dw.
Oh, okay. Yeah, okay. Makes sense.
We're just using w instead of u.
Yeah.
Which is a little extra confusing here, right? Because literally w is equal to u. So when you write wv, you're really writing u times sine, right? So typically, so often when I have a problem where I see, usually you don't see until after you've done the u sub, I would probably have gone back in this problem and been like, I'm going to use t's instead. So I probably would have been like, I'm going to do a t substitution and say t equals root x. And then I would have done all this with t. So I just said my integral was actually the integral of t cosine of t dt times 2. And then I would have done my usual integration by parts. I would have said u is equal to t and dv is equal to cosine of t. That's often the choice I make, is that if I do a u sub and then realize I have to do integration by parts afterwards, I change the variable of my u sub so that my integral doesn't have a u in it. So I can use for integration by parts.
Yeah.